Dear friends or students, this is Rajkumar. I did MSc Mathematics from Usman University in the year 1992. It may be divided in the 1A algebra part, vector algebra. This topic I am going to discuss with you. Vector algebra, సదిశలో అదిశలు, ఇది జామెట్రీకి మరియు ఆల్జిబ్రాకు సంబంధించినటువంటి విషయం. We divide this vector algebra into 4 parts. The first part of the vector algebra will be properties of vectors. Second part of the vector algebra, product of the vectors. And third part of the vectors is vector algebra under geometrical process. Vectors into geometric applications. And the fourth part, the very important, the last part will be multiple product of vectors. Multiple product of vectors. Today a small lesson about the properties of the vectors. We will start an introduction, then followed by the problems. EAPCET లో మనకు 6 ప్రశ్నలు వెక్టర్ ఆల్జీబ్రా సంబంధించినటువంటి క్వశ్చన్లు వస్తాయి. అది మీరు అదిశ, సదిశ, సంకలనం కానీ, ప్రోడక్ట్ కానీ, మల్టిపుల్ ప్రోడక్ట్స్ కానీ విషయానికి సంబంధించినటువంటి ప్రశ్నలు వస్తాయి. సో నా ఒక చిన్న మనవి ప్రతి ఒక్క స్టూడెంట్కి ఏంటంటే, మొట్టమొదట మీకు ఇచ్చినటువంటి ప్రశ్నా విభావల్లో ప్రశ్నను క్షుణ్ణంగా పరిశీలించండి. దానికి సంబంధించిన ఇన్ఫర్మేషన్ విచ్ ఐఎమ్ గోయింగ్ టు ఎక్స్ప్లెయిన్ ఇన్ ద నౌ సెషన్ ఆర్ ఫ్యూచర్ సెషన్ అప్లై ప్రాపర్లీ. మొట్టమొదట మనము వెక్టార్ ఆల్జిబ్రాకు సంబంధించిన ప్రాపర్టీస్ గురించి నేర్చుకుందాం. ఫస్ట్ డెఫినేషన్ కాన్సెప్ట్. డెఫినేషన్స్. All the physical quantities we have divided into 2 parts, may be called as the vectors and the scalars. And that physics people a little bit about pseudo vector we use it to talk, but pseudo vector that we will discuss afterwards. First of all, what is a scalar quantity, what is a vector quantity? That regarding 2 definitions if you are clear, rest of the problems easily we can come across. What is a scalar quantity? Dear students, scalar, the physical quantity which is concerned with only the magnitude, that is called a scalar. Like an example, real numbers, temperature, time, these are all the scalars which is concerned with only a magnitude. A physical quantity which is concerned with both magnitude and the direction, that we call as a vector. For example, you take velocity and acceleration, it is concerned with both magnitude and the direction, that we call as a vector. Examples of these scalars. Examples of scalars are temperature, time, okay, and real numbers. These are the examples for the scalars. And examples for the vectors. Examples for the vectors will be force, acceleration. These all the 2 examples. So in the algebra part, definitions, one more definition. First, what do you mean by magnitude of a vector? What is magnitude? Magnitude of a vector, because in the definition I explain you a physical quantity which is concerned with both magnitude and the direction we call as a vector. What is the magnitude? Magnitude of a vector is a non-zero real number which measures the length of the vector. Maybe 10 units or 15 units. That depends on the physical quantity. If you take force, acceleration, units will be different. A non-zero real number which measures the length of the vector we call as the magnitude of the vector. Generally it is denoted in a 2 parallel lines. Let r bar is equal to x times of I bar plus y times of j bar plus z times of k bar. Then magnitude of r bar denoted by two parallel lines, and it is defined by mod of r bar is equal to root of x square plus y square plus z square. Means we are giving the distance from origin to the vector r bar. Units will be differ from a physical quantity to physical quantity. That is the magnitude of a vector. First we will come across null vector. Null vector. A vector whose magnitude is 0. A vector whose magnitude is 0 and denoted by 0 bar called a null vector. Every vector quantity will be concerned with the magnitude as well as direction. I am talking about the null vector. We concluded that in the definition magnitude of null vector is 0 units. What about its direction? There is no direction for the null vector. We may call it as undetermined or indeterminate direction. It is denoted by 0 bar. And its initial point and the coincident point will be coincident. That is called null vector. For example, a vector started from a point A. It moved in a indeterminate direction. Maybe from here to here or here to here. It is called null vector. A null vector is a vector quantity whose magnitude will be 0. Direction of the unit vector, because we talked in the definition a vector concerned with the magnitude as well as the direction. What about the direction of the unit vector? The direction of the unit vector along the given vector or in the opposite direction. If a cap is equal to plus a bar divided by mod of a bar in the direction of a bar, means where the a bar direction, that unit vector plus, and a cap is equal to minus a bar divided by mod of a bar in the opposite direction of a bar. Unit vector, a vector whose magnitude will be 1 unit and the direction along the vector or in the opposite vector we call as a unit vector. For every vector there will be 2 unit vectors in the same direction and in the opposite direction. In the vector algebra geometrical concept, 3 points to be remembered. They are lines. What do you mean by lines? A line whose initial point and the terminal point is not defined, that is called a line. And second point, ray. What is a ray? Ray whose initial point is defined and the terminal point is not defined, called a ray. And the third thing, segment, line segment. Line segment, what is a line segment? A part of the line whose initial point and the terminal points are defined, called as a line segment. Vectors are said to be co-initial vectors whose initial point is coincident. Let OA bar is equal to A bar, OB bar is equal to B bar, OC bar is equal to C bar. These are the 3 co-initial vectors. Their initial point will be coincident. OA bar is equal to A bar, and OB bar is equal to B bar, and OC bar is equal to C bar. A co-initial vectors whose initial point will be coincident. We are not bothered about the terminal point. They are called co-initial vectors. We called about null vector, unit vector, co-initial vectors. Free vectors, the name itself you have noticed. In the space when you take, there are some vectors whose initial and terminal are not defined and there is no position connected. They are called free vectors. Free vectors whose initial terminal not defined, they are in the space somewhere. They are called free vectors. What do you mean by position vector? Definition of a position vector. Let O be the origin. O is the origin. O be the origin. P is a point in the space. P is a point in the space. Then OP bar is called position vector of point P. Position vector. Okay. A vector whose position connected to the origin is called a position vector. Position vector is OP bar. Collinear points are collinear vectors. collinear points and the collinear vectors. Vectors are said to be collinear vectors if they have same line of action or parallel lines of action. Collinear vectors or collinear points are parallel vectors, both of them will be same. Vectors are said to be collinear vectors or parallel vectors if they have same line of action or parallel lines of action. For example, let AB bar is equal to A bar and BC bar is equal to B bar. Two vectors connected by the point A, AB bar and B, BC bar. So, these A bar, B bar will be the collinear vectors along the line ABC, or if you take AB bar is equal to A bar and some CD bar is equal to B bar, then these two vectors will be parallel. Why do we call collinear parallel? Both of them will be equal. Its equivalent can be drawn here. That is why there is no difference between collinear and the parallel vectors. If two vectors are collinear or parallel, then one vector can be written as lambda times of other vector, and constructing a relation between these two vectors with a scalar. That is the property for the parallel vectors, where lambda is a scalar, non-zero quantity. How to add two vectors? Let AB bar is equal to A bar and BC bar is equal to B bar, two vectors. AB bar is equal to A bar, BC bar is equal to B bar, two vectors. Add addition of A bar and B bar is denoted by A bar plus B bar and defined by A bar plus B bar is equal to AB bar plus BC bar, that is equal to AC bar. And to add two vectors, terminal point of the first vector should be coincident with the initial point of the second vector. Geometrically, if you represent, let AB bar is equal to A bar and BC bar is equal to B bar, two vectors. AB bar is equal to A bar, BC bar is equal to B bar, two vectors. First vector terminal point coincident with the second vector initial point. Then the resultant vector we called as the addition of A bar plus B bar. AB bar is equal to A bar, BC bar is equal to B bar. Then AC bar is equal to A bar plus B bar. Then definitely you are getting a doubt. To add two vectors, first vector initial point, second vector terminal point should be coincident. First vector terminal point, second vector initial point should be coincident. For example, you take two vectors in the space. AB bar is equal to A bar, CD bar is equal to some B bar. Here we noticed that first vector terminal point not coincident with the second vector initial point. How to add these type of vectors? Its equivalent vector you draw here. The CD bar equivalent vector we have drawn at a point of the B bar. Now the addition can be possible. So to add two vectors, one thing to be remember, first vector terminal point should be coincident with the second vector initial point. And the addition of vectors we also called as triangular law of addition. Why we call triangular law of addition? If A bar and B bar are the adjacent sides of the triangle, A bar and B bar are the adjacent sides of the triangle, then third side is resultant of these two, A bar plus B bar. The direction of the A bar plus B bar resultant of A bar and B bar. So this is known as triangular law of addition, and addition of vectors will follows the commutative law, okay, that we are going to prove. Let A, B, C, D is a parallelogram. A, B, C, D is a parallelogram. Let AB bar is equal to A bar and BC bar is equal to B bar, two adjacent sides of the parallelogram. Now take the diagonal AC bar. The diagonal AC bar will be is equal to AC bar is equal to, according to triangular law addition or addition of vectors, AC bar is equal to AB bar plus BC bar, and that is nothing but A bar plus B bar. You called it is first equation. Its equivalent BC bar, here B bar will be the parallel in the same direction and DC bar will be B bar, A bar. Now the vector AC bar also can be added by using AD bar plus DC bar, AD bar plus DC bar. So here we notice that AD bar is nothing but B bar and DC bar is nothing but A bar in the same direction. So AC bar, this will be the second. So from first and second equation, from 1 and 2 clearly notice that AC bar will be is equal to A bar plus B bar and is equal to B bar plus A bar. So addition of vectors will follows the commutative law. Next, what do you mean by negative vector? Negative vector, what is the meaning of negative vector? If AB bar is equal to A bar, be a vector. AB bar is equal to A bar, be a vector, then BA bar is equal to minus A bar is called, BA bar is equal to minus A bar is called negative vector of vector A bar. Okay, so negative vector will be in the opposite direction of the given vector. For example, AB bar is equal to A bar, be a vector in the opposite direction, that is BA bar will be is equal to in the opposite direction minus A bar. Next, like vectors. What do you mean by like vectors? Vectors are said to be like vectors if they are in the same direction. For example, AB bar is equal to A bar and CD bar will be is equal to some B bar. They are in the same direction, not concerned with the magnitude. Vectors are said to be like vectors if they are in the same direction. Unlike vectors. What do you mean by unlike vectors? Vectors are said to be unlike vectors if they are in the opposite direction. Both like vectors and unlike vectors are concerned with only the direction, not with the magnitude. Vectors are said to be unlike vectors if they are in the opposite direction. For example, AB bar is equal to A bar and CD bar will be is equal to B bar, DC bar. It is in the opposite direction. So vectors are said to be unlike vectors if they are in the opposite direction. Both like vectors and unlike vectors will be parallel, and like vectors and unlike vectors can be expressed A bar is equal to lambda times of B bar. That lambda may be positive or negative. Both of them will be parallel vectors, like vectors and unlike vectors. How a scalar will be multiplied with a vector? If a scalar is multiplied with a vector, resultant is a scalar or a vector. If it is vector, then what will be the direction? If it is a scalar, there is no question of the direction. Okay, let A bar be a vector. L is a scalar. Generally scalar will be the real number. L belongs to R. A bar be a vector and L be any scalar. Then LA bar is a vector. Then what is the direction of the LA bar? If L is positive, then LA bar is in the direction of A bar. Scalar is scalar multiplied with a vector. Let A bar be any general vector concerned with the magnitude and the direction, and L is any scalar real number. Then LA bar is a vector quantity, and if L is positive, the direction of LA bar will be in the direction of A bar only, and if L is negative, then LA bar is in the opposite direction of A bar. Opposite direction of LA bar when L is negative. If L is equal to 0, then LA bar is equal to 0 bar, a null vector. How? An angle is defined between the two vectors. Generally, to find the angle, it is between two lines only. But a vector is concerned with the direction as well as the magnitude. Then how to get the angle? Angle between two vectors is nothing but angle between two vectors is nothing but angle between the lines where the vector lies. Angle between the lines where the vector lies. That is, let OA bar is equal to A bar, OB bar is equal to B bar, two coinitial vectors. Okay, OA bar is equal to A bar, and OB bar is equal to B bar, two coinitial vectors. Then angle between A bar and B bar is nothing but angle AOB, that is theta. Generally, angle between the two vectors written in ordered pair A bar comma B bar is equal to theta, and that is angle AOB. Angle between two vectors is nothing but angle between the lines of the vector where it lies, and it is not concerned with the direction, it is only the angle between the two lines. Okay. Next, if A bar and B bar are two vectors, then you can define in the opposite direction minus A bar. Similarly, minus B bar in the opposite direction of the B bar, minus B bar. If theta is the angle between A bar B bar vector, then the same angle will be in the opposite direction vector. In the sense, if theta is equal to angle between A bar B bar, then this theta is also is equal to between minus A bar and B bar, minus B bar. If theta is the angle between A bar B bar, then theta is also equal to angle between minus A bar and B bar. Then what is the angle between A bar and minus of B bar? A bar and the minus of B bar, or B bar and minus of A bar. Yeah, this is angle between B bar and minus of A bar. So angle between B bar and minus of A bar will be is equal to pi minus theta, and angle between minus A bar and B bar is also pi minus theta, because this is pi subtracted by theta, pi minus theta. Properties of angle between the vectors. First property, if theta is angle between A bar and B bar, then angle between minus A bar and minus B bar is also theta. Angle between A bar B bar and opposite vectors will be same. And second, if theta is the angle between A bar and B bar, then theta will be also is equal to LA bar and MB bar, where L comma M be the positive scalars. And we have extended, for example, OA bar is equal to A bar, and OB bar is equal to B bar, two coinitial vectors V2. Its length increase in the same direction, LA bar, an extended vector of A bar, and MB bar, an extended vector of B bar. Then angle between A bar and B bar and angle between LA and B bar will be same, provided L and M will be the positive real numbers. And third property, if theta is angle between A bar and B bar, then angle between minus A bar and B bar is equal to angle between A bar and minus B bar is equal to pi minus theta. Similarly, fourth property, if theta is the angle between A bar and B bar, then angle between LA bar and MB bar will be is equal to theta if L and will be negative and M is also negative. The angle between the vectors properties. And if you extend the line, angle is not going to be changed. Next coming coplanar vectors. And first a small point to be discussed. Vector and vector point. What is the difference between a vector and a vector point? Just now we have discussed P is a vector point in the space. P is a vector point in the space. Joining two vector points, a vector will be formed, some B bar. Joining two vector points, a vector will be formed. Vector points are different and vector. If AB bar is a vector, then it can be expressed, AB bar can be expressed as OB bar minus OA bar. Triangular law of addition if you take OB bar or OA bar and AB bar, OA bar and AB bar, then OB bar will be is equal to OA bar plus AB bar. Triangular law of addition. So, OB bar is equal to OA bar plus AB bar. Therefore, AB bar can be written as OB bar minus OA bar. So, position vector of AB bar will be is equal to position vector of B bar minus position vector of A bar. Or you may write AB bar is equal to OB bar minus OA bar. This is the triangular law of addition and expressing in the position. Now, to define the coplanar vector, we have started a vector and a vector point. P and Q are the vector points. Joining two vector points, a vector will be formed. Two vectors always construct a plane. If A bar and B bar, two vectors, it construct a plane. So, to talk about the coplanarity of the vector, it should be more than two or three vectors. Vectors are said to be coplanar vectors if they lies in the same plane or parallel planes. One thing should be remember that more than two are, in the sense three or more vectors are said to be coplanar vectors if they lies in the same plane or parallel plane. For example, plane is always denoted by pi is equal to 0. Consider one plane, pi is equal to 0, a plane pi. Three vectors A bar and B bar, C bar. If they lies in the same plane, then we call these three vectors are coplanar. Vectors are said to be coplanar vectors if they lies in the same plane or parallel plane. Consider three planes, pi 1 is equal to 0, a plane which is in the A bar, and pi 2 is a plane which is parallel to pi 1, and pi 3 is a plane which is parallel to pi 2. Pi 1, pi 2, pi 3, three parallel planes, A bar here and B bar here and C bar. So, you can construct one plane passing through these A bar, B bar, C bar, then we call they are also coplanar. Pi 4 is a plane which is constructed by A bar, B bar, C bar. So, vectors are said to be coplanar vectors if they lies in the same plane or parallel planes, that is the coplanarity. Just now we have defined coplanar vectors. Condition for the vectors to be coplanar. To give before that one a small definition, linear combination. What do you mean by linear combination? Expressing a vector with the help of the scalar on the addition process, combination. Expressing a vector with the help of the scalar in a combination is called linear combination. Example, a vector r bar is called linear combination of A bar, B bar and C bar if there exist scalars x, y, z such that r bar is equal to x times of A bar plus y times of B bar plus z times of C bar, This R bar is called linear combination of A bar, B bar, C bar constructed by x, y, z scalars. This is called linear combination. Expressing a vector in the combination of other vectors with a scalar is called a linear combination. Okay, three vectors A bar, B bar, C bar said to be coplanar vectors if one vector expressed a linear combination of other two vectors uniquely. Let A bar, B bar, C bar three coplanar vectors. Then the vector A bar can be expressed linear combination of B bar and C bar uniquely. The combination of A bar expressing B bar and C bar uniquely. This is called linear combination. No rule that A bar only should be in terms of B bar and C bar, or the vector B bar can be expressed x times of A bar plus y times of C bar uniquely. What do you mean by uniqueness? Construction of the system of lines to be discussed here. A vector R bar, C bar, B bar is equal to x A bar plus y C bar, or C bar is equal to x times of A bar plus y times of B bar. Then we call that three vectors A bar, B bar, C bar are coplanar. Condition for the three vectors to be coplanar is expressing a vector in the linear combination of other two vectors uniquely. These until there exist a unique values of x and y satisfying the linear combination, then we call coplanar. Or the next concept we are going to discuss in the multiple product. Three vectors A bar comma B bar comma C bar are said to be coplanar vector if their box value will be is equal to 0. Condition for the three vectors to be coplanar is either express the first vector linear combination of other two uniquely, or the box value is equal to 0. Regarding this box, everything we will discuss in the coming future topics. This is condition for the vectors to be coplanar. What do you mean by direction cosines? In the geometry, regarding a straight line, inclination of the line we have discussed. But the vectors in the triad we are talking about the space. For example, let R bar is equal to xi bar plus yj bar plus zk bar. Consider a vector. What is the meaning of this one? R bar is a vector, component of R bar along the x axis x units, y units and z units. It is written in ordered x is equal to x comma y comma z. Triad in the space. What are I bar, j bar, k bar? I bar, j bar, k bar are the unit vectors of coordinate axis. For example, you take the space system, x axis, y axis and z axis. Three mutually perpendicular lines. I bar is the unit vector of x axis, j bar is the unit vector of y axis and k bar is the unit vector of z axis. A vector point R bar written in x comma y comma z. What is the meaning of this one? The vector R bar is equal to x times of I bar, y times of j bar, z times of k bar. The component of R bar along the x axis x units, along the y axis y units, along the z axis z units. Okay, why we have discussing to start the direction cosines? Position of the vector in the space explained to you. What is the inclination of the straight line? An angle made by the line with x positive axis in the anti-clockwise direction we called as the inclination. Then we define slope of the straight line. But here direction cosines in the vector. And when you take a space giving a direction to that vector, that is called direction cosines indirectly. I will tell you the mathematical definition. If alpha, beta, gamma angles made by a vector R bar with coordinate axis x axis, y axis, z axis respectively. R bar be a vector in the space, angles made by R bar vector with coordinate axis x axis, y axis, z axis are alpha, beta, gamma, then cosine of the angles cos alpha, cos beta, cos gamma called direction cosines of R bar. I will repeat the definition of the direction cosines. alpha, beta, gamma angles made by a r bar vector with coordinate axis, then cosine of the angles cos alpha, cos beta, cos gamma are called direction cosines of r bar. For example, you take coordinate axis, O be the origin, x axis, y axis and z axis, okay, and let OR bar be a vector. Then angle made by r bar vector with x axis will be alpha and y axis will be beta and z axis will be gamma. Alpha, beta, gamma, then cos alpha, cos beta, cos gamma we called as the direction cosines of r bar. Generally they are denoted by L, M, N. Direction cosines of r bar, that is L, M, N will be is equal to cos alpha, cos beta, cos gamma. If L, M, N are the direction cosines of r bar vector, then they satisfies one property, that is L square plus M square plus N square is equal to cos square alpha plus cos square beta plus cos square gamma will be is equal to 1. If it can be changed into the sign of the angles, cos square alpha can be written as 1 minus sin square alpha and cos square beta will be 1 minus sin square beta, cos square gamma will be 1 minus sin square gamma is equal to 1. On taking sign of the angles right side, then it will be 3 minus 1 is equal to sin square alpha plus sin square beta plus sin square gamma. So, the result sin square alpha plus sin square beta plus sin square gamma will be is equal to 2. If L, M, N are the direction cosines of r bar, then L square plus M square plus N square is equal to cos square alpha plus cos square beta plus cos square gamma equal to 1 and sin square alpha plus sin square beta plus sin square gamma is equal to 2. This is direction cosines of a vector. Alpha, beta, gamma are the angles made by r bar with coordinate axis. Then what will be the angles made by r bar in the opposite direction, or you may take minus vector. R bar be a vector, angle made by r bar with the coordinate axis alpha, beta, gamma. Then what will be the angles made by minus r bar, or you may call negative vector with the coordinate axis, that will be pi minus alpha, pi minus beta, pi minus gamma. Then when you take direction cosines of opposite vector, they are also L, M, N will be is equal to cos of pi minus alpha, cos of pi minus beta, cos of pi minus gamma. We know that cos 180 minus theta is equal to minus cos theta, then minus cos alpha minus cos beta minus cos gamma, means if L, M, N are the direction cosines of r bar vector, then minus L minus M minus N will be the direction cosines of same vector in the opposite direction. Okay? For every vector there will be two direction cosines in the same direction in the opposite direction. How many vectors in the space will make equal angles in the coordinate axis? That is, let r bar be a vector makes equal angles with axis, that is alpha is equal to beta is equal to gamma. My question, how many vectors in the space will make equal angles in the coordinate axis? To r bar be a vector, it makes equal angles with the coordinate axis, that is alpha is equal to beta is equal to gamma, means cos square alpha plus cos square beta plus cos square gamma is equal to 1. As alpha equal to beta is equal to gamma, it will be cos square alpha plus cos square alpha plus cos square alpha is equal to 1. So, 3 cos square alpha equal to 1. So, cos alpha is equal to 1 by 3 cos square alpha, cos alpha is equal to plus or minus 1 by root 3. Okay. So, if you express in the direction cosines L, M, N will be is equal to plus or minus 1 by root 3 plus or minus 1 by root 3 plus or minus 1 by root 3. Taking plus 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 minus 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 a vector and it is in the opposite, plus plus minus minus plus plus same vector, means there will be total 8 vectors in the space makes equal angles with the coordinate axis. What do you mean by linearly dependent vectors? Set of vectors are said to be linearly dependent vectors if there exists set of scalars such that L1 A1 bar plus L2 A2 bar plus L3 A3 bar Ln An bar is equal to 0 bar, then we call that set of vectors are linearly dependent. I will repeat the definition with notes. Set of vectors A1 bar, A2 bar, A3 bar and so on up to An bar said to be linearly dependent vectors if there exists set of scalars L1, L2, L3, Ln such that L1 into A1 bar plus L2 into A2 bar and so on up to Ln into An bar is equal to 0 bar, then we say A1 bar, A2 bar, An bar are linearly dependent vectors. Example for the linearly dependent vector, just now we have seen all parallel vectors can be expressed A bar is equal to lambda times of B bar and L1, L2, Ln together not equal to 0, they are together not equal to 0. That set of vectors we called as linearly dependent vectors. Just now we have seen two vectors are parallel, one vector can be written lambda times of other vector. So, A bar is equal to lambda times of B bar, it can be written as A bar plus minus lambda into B bar is equal to 0 bar. This is the linear combination. So, all the parallel vectors are linearly dependent. And another example, second example, all coplanar vectors are linearly dependent. Just now we have seen one example, a vector A bar, B bar, C bar said to be coplanar, one vector expressed a linear combination of other vectors, that is A bar is equal to x times of B bar plus y times of C bar, then we called A bar, B bar, C bar are coplanar. So, A bar can be written as minus x times of B bar plus minus y times of C bar is equal to 0 bar, where 1 is not equal to 0. So, it is constructed by the relation linear combination. So, all the coplanar vectors are linearly dependent, all the parallel vectors are linearly dependent. Set of vectors are said to be linearly dependent vectors if there exists a set of scalar, their linear combination equal to 0 and all the set of scalars together not equal to 0, they called as linearly dependent vectors. Set of vectors are said to be linearly independent vectors if their linear combination, that is L1 into A1 bar plus L2 into A2 bar plus L3 into A3 bar and so on up to Ln into An bar is equal to 0 bar, then L1, L2, Ln together equal to 0, they are called linearly independent. So, all the vectors are either linearly dependent vectors or linearly independent vectors. All non-parallel vectors are linearly independent. All non-coplanar vectors are linearly independent. For example, you take in the space I bar, J bar, K bar, they lies in the different planes. So, I, J, K will be linearly independent vectors together. Linearly dependent vectors, linearly independent vectors. In the first session, definition and a small problems point of view, we will start in the next session regarding the definitions and formulas. Once again we will glancely revise, then we will start the problems. Okay. First we have come across the definition of the different vectors and addition of the vectors, properties of the addition of the vector, parallelogram law of addition of the vectors and angle between the vectors, a scalar multiplied with a vector, linear combination, linearly dependent vectors, linearly independent vectors, direction cosines of a vector. These are all the concept a little bit we have discussed time point of view, and we will start the problems based on this concept. OA bar is equal to AB bar is equal to BC bar is equal to CD bar, then tell me the position vector of T bar. A small concept to be discussed, in every closed polygon the vector sum is 0, in the sense For example, construct a triangle ABC with the vectors A, B, C. A to B is the direction, B to C and C to A. This is a closed polygon. In every closed polygon, the vector sum is 0. So, AB bar plus BC bar plus CA bar. If you take AB bar plus BC bar, whose initial and terminals are coincident, you can write as AC bar and CA bar. And here again the initial and coincident. So, CC bar. So, AA bar is equal to 0 bar. In every closed polygon, the vector sum will be 0. You may take triangle or you may take quadrilateral. Consider one quadrilateral ABCD. In this one closed polygon ABCD, closed polygon means whose initial point, terminal point will be coincident. So, their directional sum AB bar, BC bar, CD bar and DA bar. Again here also AB bar plus BC bar plus CD bar plus DA bar will be is equal to 0 bar. So, if you take any closed polygon, the vector sum will be 0. Now, our problem is given that OA bar is equal to A bar. OA bar is equal to I bar plus J bar plus K bar. And AB bar is equal to 3 times of I bar minus 2J bar plus K bar. BC bar is equal to I bar plus 2J bar minus 2K bar. And CD bar is equal to 2I bar plus J bar plus 3K bar. I want the position vector of D bar. Position vector of D bar is OD bar. So, to get OD bar, connectivity of the points we have noticed, that is OA bar plus AB bar plus BC bar plus CD bar. So, OA bar plus AB bar, this is connected, which is nothing but OD bar, and the resultant of all these vectors is OD bar, that is 3I bar plus I bar, and which is 6 times of I bar, and minus 2J plus 2J cancel, that is 2 times of J bar, and minus 2K plus 2K, which is 3 times of K bar. So, the vector OD bar will be is equal to 6I bar plus 2J bar plus 3K bar. Only the position vector, if he asked, find what is the mod of OD bar, find its length also. So, the mod of OD bar is equal to, just now we defined R bar is equal to Xi bar plus Yj bar plus Zk bar, then mod of R bar is equal to root of x square plus y square plus z square. So, mod of OD bar is equal to square root of 6 square plus 2 square plus 3 square, and which is nothing but square root of 36 plus 4 plus 9, which is 49. 49 root will be is equal to 7. So, we calculated the position vector of D bar and its magnitude will be is equal to 7. If the position vectors of 3 points A comma B comma C are I bar plus 2J bar plus 3K bar, J bar plus 2K bar, minus I bar plus K bar, and it satisfies AB bar is equal to lambda times of AC bar, then tell me lambda. Position vectors of 3 points is given, and the combination AB bar is equal to lambda times of AC bar. So, AB bar and AC bar will be parallel or collinear, then find lambda value. According to the position vector, here OA bar, given that OA bar is equal to I bar plus 2J bar plus 3K bar, their position vectors writing OB bar is equal to J bar plus 2K bar, OC bar is equal to minus I bar plus K bar, and it satisfies a relation AB is equal to lambda times of AC. Substitute AB bar is equal to lambda times of AC bar, that in the sense OB bar minus OA bar is equal to lambda times of OC bar minus OA bar. Tell me lambda value. Okay, OB bar is nothing but J bar plus 2K bar minus OA bar I bar plus 2J bar plus 3K bar will be is equal to lambda times of OC bar minus I bar plus K bar minus OA bar. OA bar will be I bar plus 2J bar plus 3K bar. Apply the vector addition and subtraction. So, J bar, it is minus I bar, J bar minus 2J bar minus J bar, 2K bar subtracted by 3K bar. minus k bar is equal to lambda times of minus I bar minus 2 I bar, and it will be minus 2j bar k bar minus 2 times of k bar. Now, as we noticed that ijk are linearly independent, equalating their coefficient wise, minus 1 is equal to minus 2 lambda. This implies lambda is equal to 1 by 2. For lambda is equal to 1 by 2, we called A bar, B bar, C bar will be the parallel. 3 points A, B and C, their position vectors are 1 comma x comma 3, 3 comma 4 comma 7 and y comma minus 2 comma minus 5 respectively. And if they are collinear, then tell me the ordered pair x comma y. If A comma B comma C are the collinear, so AB bar will be is equal to lambda times of AC bar. As we expressed in the position vector, OB bar minus OA bar is equal to lambda times of OC bar minus OA bar, and that is OB bar 3I bar plus 4J bar plus 7K bar minus OA bar I bar plus x times of j bar plus 3 times of k bar is equal to lambda into, now again we will calculate lambda value, OC bar y times of I bar minus 2j bar minus 5k bar subtracted by OA bar. OA bar will be I bar plus x times of j bar plus 3 times of k bar. Just now we have discussed that I, j, k are linearly independent. So, linearly independent vectors are expressed in the combination to equalate it to 0. Their scalars, on equalating we noticed that I bar component wise 3I bar subtracted by I bar 2I bar and 4j bar subtracted by xj bar plus 4 minus x times of j bar and 7k bar subtracted by 3k bar, that is 4k bar is equal to lambda times of yi bar subtracted I bar, that is y minus 1 into I bar minus 2j subtracted by xj bar, that is minus 2 plus minus x times of j bar minus 5k subtracted by minus 3k minus 8 times of k bar. Okay. On equalating their lambda component wise, 4 is equalated to coefficient of 8k, that is lambda into minus 8. Therefore, lambda is equal to 4k is equalated to lambda times of minus 8, equalating coefficient of k bar. Then lambda is equal to 4 divided by minus 8, lambda will be is equal to minus 1 by 2. Okay. On equalating the coefficient of I bar, 2 is equal to lambda times of y minus 1. Substituting lambda here, 2 is equal to minus 1 by 2 times of y minus 1. So, minus 4 is equal to y minus 1. So, y will be is equal to minus 4 plus 1, which is y is equal to minus 3. Lambda will be minus 1 by 2, y equal to minus 3. To get x value, equalating the j bar coefficient, 4 minus x j bar coefficient equalated to lambda times of minus 2 and minus x. Substituting lambda minus 1 by 2, 4 minus x is equal to minus 1 by 2 times minus 2 minus x. On solving, 8 minus 2x will be is equal to 2 minus 2 plus x, or 6 is equal to 3x. Therefore, x equal to 2. So, x equal to 2 and y equal to minus 3. The ordered pair x comma y will be is equal to 2 comma minus 3. Here we have noticed that the points a comma b comma c are the collinear points. So, x is 2, y equal to minus 3. Today we concluded that problems based on the collinear points, coplanar points, parallelity, definitions, unit vector